All right, let's go ahead and get started. I want to welcome you back to Unit 8, the mole. And actually, in this final screencast, we're not going to be looking at anything new. I just want to make sure that we understand these concepts and that as we move on to stoichiometry, that we understand the mole perfectly. So I want to talk a little bit about, again, the difference between the empirical formula and the molecular formula. So remember, the empirical formula is the simplest whole number ratio, right? That's it. It doesn't mean that it's the actual molecule. It could be, but it doesn't necessarily mean that it's the actual molecule. There's a molecule called benzene. It has this molecular formula. It's C6H6, just like that. But if this is the molecular formula, how it actually exists, then the molecular formula is this. We're going to divide both 6 and 6 by 1, and we get CH. So that would be the empirical formula, okay? So let's make that comparison. Empirical formula is the simplest whole number ratio, and then, of course, the molecular formula is the actual molecule itself, all right? And sometimes, often, we're going to see that they are one and the same, so that as if we, for example, look at the water molecule, which is H2O, right? That's the empirical formula, but it's also the molecular formula. It's actually the way that the molecule exists in nature. So the Lewis structure would be something like this, right? So that hopefully clarifies that difference between empirical formula and molecular formula. Let's go over a couple of examples again that we've already looked at actually, but I just want to make sure that we've got this. In this first one, we looked at the molar mass of butane, and we said that it was 58.14 grams. So that's the actual molecule, right? The actual molecule. Butane, by the way, is a molecule that has this Lewis structure. It's going to be 4 carbons, just like this. 1, 2, 3, 4. And then there's going to be hydrogens all around it. Folks, this is an organic molecule, and very often we don't write the actual hydrogens in. Everywhere you see one of those little dashes, that indicates that there's a hydrogen there, right? So it's C4. Butane, the empirical formula is C2H5, right? C2H5. And they want to know what the molecular formula is for this molecule, right? So how do we determine that? Well, what we're going to do is we're going to look at the molar mass of the empirical formula, just the basic formula. This is not the basic formula. I said this is butane. This is the molecular formula. So the empirical formula is the simplest whole number ratio, and I'm told it's a 2 to 5 ratio. So what I did was I simply multiplied the 12.01 for the carbon and the 1.01 for the hydrogen by 2 and 5 respectively. When I add those up, I get this number, 29.01. But again, that's the number of grams of the empirical formula, a molecule that may not exist, right? So they're also telling me the molar mass, the mass of 1 mole of this compound called butane, is 58.14, right? They're saying that it has a mass of 58.14. So that's twice approximately, in fact, exactly twice the mass of the 29.07 of the empirical formula. That must mean that the molecular formula is twice as big. So if the empirical formula is C2H5, the molecular formula would be twice that, C4H10. Okay, C4H10 then would be the molecular formula. All right. So we looked at that example, and then we talked a little bit about this compound that had carbon and oxygen and hydrogen, or carbon and oxygen rather. And the empirical formula was what we were looking for, and they gave us these values in grams. Okay, so remember when we write a compound, say for example, I'm just making this up. If I say CO2, that's a mole to mole relationship, right? Not a gram to gram relationship. So I don't have twice as many grams of oxygen as I do carbon, but I do have twice as many moles of oxygen per mole of carbon, right? So the first thing I did was I made the conversion to moles. So I got this number, 2.27 and 4.54 for the number of moles of carbon and oxygen, and you should be able to do that dimensional analysis pretty easily. Remember that these are going to cancel here and here, and so then what we're going to be left with is the mole ratio. It's obviously a 1 to 2 ratio, and so that means that the empirical formula is going to be 1 carbon for every 2 oxygens. So the empirical formula must be CO2, right? So that's the technique that we've used to find that empirical formula. Good. In example 3, we looked at this. We did an analysis of a compound that had lithium, hydrogen, and phosphorus, and oxygen. So 4 different elements, right? And they were the percentage, right? They were in percentage form. So what we did was something that was very clever. We assumed a 100-gram sample, right? We assumed a 100-gram sample. We have 6.64, 1.92, 29.8, and 61.6 respectively. What I did was I assumed a 100-gram sample so that I could convert those directly to grams, right? So now those percentages get converted to grams. Now that's still not good enough because remember, in the empirical formula and the molecular formula for that matter, it's a mole to mole to mole to mole relationship, not gram to gram to gram to gram. So I've got another step, and that is to take those grams of lithium, hydrogen, phosphorus, and oxygen respectively, and remember what I did was I converted those to moles, right? Again, dimensional analysis. Grams will also always cancel with grams. I'm getting these numbers off the periodic table, right? Off of the periodic table. So now what I've got is the mole to mole to mole to mole relationship. And what I'm going to do now is I'm going to divide by the smallest of these numbers. It turned out to be the 0.96 here and here. And so I divided by the 0.96, remember? And when I did that, I got this 1 to 2 to 1 to 4 mole to mole to mole to mole relationship. And I was lucky that they're all whole numbers, because if they're not whole numbers, I have to multiply by 2 or multiply by 3 or whatever I need to do. But this is pretty straightforward. 1, 2, 1, 4. That's the mole to mole to mole to mole relationship. Okay? So that's that. Now, from these molar mass ratios, I can determine the empirical formula. Right? Again, it's 1 to 2 to 1 to 4, so the empirical formula then turned out to be LiH2PO4, right? So that gave me that empirical formula based on those. Originally, they were just percentages. Then we turned it to grams. Then we turned them to moles. And now we've got the empirical formula, okay? All right. Then in this next example, example 4, we looked at a compound and we determined that it was some percentage, 49.3% carbon, 6.85% hydrogen, 43.8% oxygen, right? And they were giving me, this time, the molar mass, the weight of 1 mole of this molecule containing carbon, hydrogen, and oxygen, right? And they said, what is the molecular formula now? So I can do more than just find the empirical formula because I've got an additional piece of information. I've now got that molar mass. So this problem requires that we not only obtain the empirical formula, but we use the molecular weight to obtain the molecular formula as well, right? So how do we do it? Well, what we're going to do is we're going to go do exactly the same thing. Assume a 100-gram sample, convert from percentages to grams. I did that here. So now I've got grams. Now it's still not good enough. I need to convert those to moles using simple dimensional analysis. Convert those to moles, and I've got these numbers, right? 4.10, 6.78, 2.74. What do I do next? I divide by the smallest one, the 2.74, right? So find 2.7, or divide everything by 2.74, and when I do that, I get 1.5, 2.5, and 1. Uh-oh, I've got fractions. In fact, I've got 1.5 and 2.5. Now, when that happens, the way to fix that is to multiply everything by 2. Everything, even the 1, by 2. And when I do that, 1.5 times 2 is going to give me 3, right? 2.5 times 2 is going to give me 5, and 1 times 2 is going to give me 2. So it becomes a 3 to 5 to 2 ratio, 3 to 5 to 2 ratio. So now I know the empirical formula, all right? But that's not what we were looking for. That was the empirical formula. I was looking for the molecular formula. So let me add up the weights of the 3 carbons, the 5 carbons, and the 2 oxygens. When I do that, I get the 73.08. Now, let me compare that number to the 145 grams per mole that I was given. All right? Well, it's about, right, twice the empirical formula. So 145 is about twice 73.8. So what I'm going to say is that the molecular formula is twice the empirical formula, or this number, or this value, C6H10O4, and that'll do it for that example, right? That's how we arrived at that molecular formula. We went on to example 5, where we said boron was one of these 4, right? And they gave me the percentages of, they gave me actually the percentage of boron, but not hydrogen. I did simple subtraction. 100% minus 81.1% gave me the percentage of oxygen. So now I've got it in percentage. So now I can convert that by assuming a 100 gram sample. I can convert that to grams. So if I've got a 100 gram sample, it's 81 grams of boron and 18.9 grams of hydrogen. Now convert that to moles like I did before. The smaller of these two is going to be the 7.50. So I'll divide both by 7.50, and here's what I get. I get 1.00, and I get 2.49, or about 2.5, right? Or about 2.5. Now, what do I do with that 2.5? Multiply it by 2. That's going to give me 5, but I'm going to multiply this by 2. Whoops, I'm going to multiply this one by 2 as well, right? So let me do that. Let me multiply both of them by 2. So times, let me get the right instrument here. I'm having trouble. There we go. We're going to multiply this one by 2, but we're going to multiply this one by 2 as well. So we get 2, right? So it's a 2 to 5 relationship. So the ratio of boron to hydrogen is 2 to 5, right? 2 to 5. So the only thing it could be, the only thing, but if you look at A, B, C, and D, the only thing that is a ratio of 2 and 5 is 4 and 10. So B then has to be the correct answer, right? B has to be the right answer. Then we went on to example number 6. We looked at this example of bronze that was composed of copper and tin, and we knew the mass of the entire bronze metal was 12.5 grams. So we could determine by mass how much we were talking about with regard to tin. If it's 12.5 grams total and 33% of it is tin, then that's 4.13 grams of tin right there. Then what we did was we converted that into atoms, right? There was a two-step process. We went from grams to moles, moles to atoms. And we've got this number, 2.09 times 10 to the 22nd 10 atoms, right? So that was that. We looked then at percent water in a hydrate. So remember, water in a hydrate means this. You have a molecule, in this case it's iron chloride, but it has 4 water molecules associated with it, right? 4 water molecules together with it. And so what we want to do is we want to determine the percent by mass, right, of water in this hydrate. So we can look at it like this. We can take the 4 waters, just like this, and the mass of those 4 waters, and we can do this. We have FeCl3, okay, times, or not times, but associated with 4 waters just like that, times 100, right, times 100 just like that. Does that make sense? All right, so here we go. We've got 23.431 grams per mole. That's for the iron, the chlorine, and the water is the total. We'll divide the total just by the water, 72.08, divided by 234.31 times 100, and we get this percentage of water. And that's how we took care of that problem right there. Okay. Let's see. We went to percent composition, right? Determine the number of, the number of oxygen atoms in 96 grams of carbon dioxide. So what we did here was we just did a dimensional analysis where we said, okay, if we're going to start with 96 grams, then what we're going to do is we're going to convert that to moles. Notice the mole to mole ratio of oxygen atoms to CO2 was 2 to 1. There's 2 oxygens per 1 mole of C, and then we converted that to atoms by using the 6.02 times 10 to the 23rd, and here's what I get. 2.6 times 10 to the 24th atoms, okay? Folks, I'm going to end this here. I think that gives us a little bit better of an overview of what we need to know in this last of these examples. So I'll see you on the next unit. Thanks. Bye-bye.